So in this video, we're going to show MGPUSim. We're going to show why MGPUSim is a one-stop solution for GPU simulation. So in this video, I'm going to go through with you how to install the environment for running MGPUSim, how to run a simple simulation, and how to run multi-GPU simulations, how to run different simulation in different execution mode, and also how to run the visualization tool. So I currently have a newly installed system. This is a Ubuntu 20.04 that is freshly installed on a in VirtualBox. So it's a fresh installation. It doesn't have any tool installed. So the thing I need to do first before I want to execute the first simulation is I need to install the Go environment. So we need to go to use our browser. Then in browser, we're going to first go to the Go language website, which is golang.org. Then we're going to download Go. In this case, we're going to download the Linux version of the Go environment. So we can download Go. We can save the file. Then in this file page, we have the command that can guide us install the Go command. So what we can do here is we can open a terminal. Then in this terminal, we can go to the download folder. Now we see the Go is installed here. Then we can enter it using this command. So remember, we need to use sudo command and to install to execute this command. I need to change the version. So I need to change it to Go 1.5.7. Okay, so this process is installing the Go command. Then the next thing we need to do is to provide a path for, we need to add the Go executable to the path environment variable. So what we can do here is that we can modify the bashrc file. Vim is not installed, so let me install. Let's install Vim and Git. We're going to use Git soon. Okay, so we have Vim installed. Let's add the bashrc. At the end of the file, we're going to export path as the original path plus this location. This location is at user local go and bin, like what it's doing here. So USR local go and bin. So we're going to quit it, source it to make it take effect. Then we can run Go and version. Let's see which version is installed. Okay, so Go version 1.15.7 is installed. So we have the Go environment. The next thing we need to do is to start to compile the simulation. So I mean, compile the simulation, typically what you would think is to download the simulator and install it. But using MGPUSim, you actually do not need to install it. So let's create a folder here. Let's make a folder that's called MGPUSim experiment. Then let's cd into it. MGPUSim experiment. what you need to do here is let's go from here to where MGPUSim is hosted. So it's hosted in gitlab.com Akita MGPUSim. So I'm now signed in, and so this is a fully open source project. What you can do is you can go to samples, and there's one folder called experiment. Then I think you cannot download only this folder. So what I can do here is let's download the whole repository. Okay, let's download the zip as the whole repository as a zip file. Okay, so it is downloaded. So actually we're downloading the whole repository, but we're not going to use the whole repository. So we can unzip it. Then we're going to find this folder called samples experiment. Then we're going to copy all the Go file in this folder to the folder that we just created. Let's go to MGPUSim experiment. Let's create a new folder called experiment. Now we copy everything here. We paste everything to the new folder. Paste. Okay, so we have pasted. But before we can compile it, one thing we need to do here is we need to declare this repository, this folder as a Go module. So we need to declare it as Go mod, assuming this folder is hosted on GitLab. So I'm going to use this this name, gitlab.com as Yifan. This is my username, and I'm going to name it this repository as MGPUSim experiment. We need to create it as Go mode init. Now, okay, so we're creating a new Go module, and when you ls, you can see the go.mod file is generated. Now, in the experiment folder, you can simply run go build. So you actually do not need to install MGPUSim. You simply run go build. It will automatically download MGPUSim and all other dependencies. You do not need to run apt-get for anything. You just need to compile it. So see here, it will actually download MGPUSim, the memory module, and all the other dependencies from GitLab or GitHub. Then it will compile the whole simulator with the experiment. So it's going to take some time to compile, but compared to other simulators, the compilation time is extremely short. So considering this process is actually downloading the whole dependency tree and is compiling the benchmarks and also including the whole simulator. So like less than 1 minute time, the whole simulator is compiled. And we can see here, we have this experiment and we have this experiment executable file that is generated. So a typical workflow that how we use it is we have this experiment executable here. Now in our personal computer, we typically only run short experiment so that we can guarantee it's working. Then we will copy this experiment executable to a server. So then we can run large scale simulation on a server. In this way, we do not even need to install the Go environment on the server, and we can just simply prepare the experiment and send the experiment to a server. And sometimes you can also do cross compilation. So for example, if I'm using a Mac, then I can run experiment on my Mac, then I can cross compile it for a Linux environment, then I can upload to the server. So let's take a brief look at what the experiment is doing. So we can look at the main file. Okay, this main file.go is implemented in the Go program language, and the whole MGPUSim is implemented in the Go program language. So you may not have good knowledge about the Go program language, but at least probably you can understand what is going on here. So we have a main function, and in this main function, we have a big switch case. And in this case, we only have an FLR. So the benchmark name is FLR, and we're going to support this FLR benchmark. Now, other than FLR, we support like around 20 benchmarks right now. Now in this benchmark, we can we create a new benchmark, then we add this benchmark to runner. The runner will actually is a combination of the benchmark and the hardware and the simulation. So add this benchmark to the runner, and the runner will run it. Okay, so that's for the demo purpose. Let's make this FR much shorter. Let's only have 64 single precision floating point numbers. Then let's run it and see what's going on. So we save the file, we can run go build to compile it again. And you can see this time the compilation time is much faster because we're not downloading everything, and we're not downloading that the libraries that we do not need to rebuild those libraries. And we run experiment with -h for help, and we can see what type of options that do we currently support. For example, we support benchmark. This is in the main folder, in the main function. If you want to add main benchmark, you can prepare your experiment to be able to support multiple benchmarks. Then debug ISA will generate ISA debugging file so that it will dump the instruction execution result and the register state after each execution. Then these GPUs, and also there's another one called unified GPUs, they're used together to allow multi-GPU simulation. Then we support max_inst, which is you can specify, say, I want to run 1 million instructions, then I want to stop the simulation. Then you can terminate the simulation after the given number of instructions. Then matrix file, and with this report cache hit, report cache latency, you can see what type of information we can report. And all this information that is reported is dumped in this matrix file. Now by default, we have a progress bar. You can turn it off. Now by default, we run it in serial mode. You can run it in parallel mode. It's toggle parallel mode, and serial mode is just using argument, and you can decide it in at runtime. And also timing. If you do not run timing, the simulation will run in emulation mode, so you will not get the execution time. You can only get the instruction trace. Then trace_mem is a tool that can help you trace all the events in the memory system, like what address is read in the L1 cache, what address is accessed in the L2 cache, and in the main memory. And finally, trace_viz is to trace the whole simulation for the visualization purposes. And for trace_viz end is to and trace_end start. That means if you want to specify, say, I want to trace for a short period of time, or I do not want to generate a trace for the whole simulation, you can trace it for a short period of time. Then we talk about unified GPUs. Using unified memory means when we use multi-GPUs, we allow page migration. And we, by default, we support first touch page migration, which means the page can only be migrated once to a destination GPU. And verify. So for each benchmark, we have compiled a GPU mode so that it can be run in the simulator, and it will also be run in a Go code in the CPU so that we can compare if the simulation is generating the correct result. If this verify cannot pass, your design, your modification to the hardware may not be valid because it can generate some wrong result. So this is the argument that we support. So let's run it and see what's going on. So we can run experiment. Let's intentionally create a wrong input. So that's just with timing. So you probably always want timing to get the overall timing result. So if you run timing, it will generate a wrong result because we didn't specify which benchmark to run. So we need to specify benchmark, which equals to FR. This is the benchmark we want to run. Then we run timing. You can see it runs super fast, and then it almost stops as a blink of time. Then there's this 1 out of 1. So this one is the number of work group that we need to run. So work group is like a block in NVIDIA terminology. And we use the finished work group to serve as this progress bar, so that at least when you run it, you know if the simulation is hanging or the simulation is still making progress. So see what metrics we can generate by default. So let's see, when we run ls, we see one file is generated here, but it's not here before. It's called matrix.csv. So we can open it. Matrix.csv is dumped in a CSV format, so it's separated by these commas. And this is the first column is the index, and there are 3 real columns that carries information. So these 3 information is where and what and the value. So where it happens. So we track this driver. We track this the time. We track this time at the driver side. Now we see what is going on. So you can see this driver can see a total time that is I think that is 13 microsecond to 35 nanosecond. So this time is always represented in second. So you can see at GPU1 side, this is a command processor. Command processor is connecting the driver and the GPU. You can see how long time it takes to run this kernel. This kernel takes, say, 90 or 9 microseconds to run. And why there's a difference between the driver total time and this GPU's kernel time? That means we also consider the data transfer. We transfer data from the CPU side to the GPU side. So, and when the kernel completes, we transfer the data from GPU side to the CPU side. So that's where the time difference comes from. So that is not all the metrics we can generate by default. We can generate more metrics. Say we can run the same experiment, but with more argument. Let me move this a little bit smaller. Okay, so we can use this report all to report more information. Typically, I do not find capturing those metrics are like slowing down the simulation. So typically, I would always add this report all flag. Then we can open it as vim matrix.csv. Now we can see, okay, here we have this instruction count. So what does this mean? This is GPU1 SA0. SA is shader array. Shader array is a group of 4 compute unit and with its attaching L1 caches. Then the instruction count. So this particular compute unit executed 392 instructions, and no instructions executed in other GPUs, in other compute units. Then we can look at, so it's reporting all the components and the instruction count. By default, we generate 4 GPUs. And here we have GPU1 SA0, shader array 0, it's L1I cache, the instruction cache. And we have this request average latency. This is the latency, that average latency that for in request gets into the L1 cache, L1 instruction cache, and also L1S cache, L1V cache. And also the request average latency for every L2 cache. You can see the latency is, it's around 8 nanoseconds, which is quite fast. Then we can see this one report how many transactions of different type. For example, we have this read heat. There's 74 read heat, 5 read miss. Probably is just because the first time we access it. And we have another case called MSR heat. So MSR heat is considered a miss, but it's not as expensive as a regular miss. So we report how many cases are there in these 3 categories for every cache unit, including L1 cache, L1 V cache, vector cache, scalar cache, instruction cache, and all the auto caches. Then we have this RDMA engine so that they dominate the GPU to GPU communication. Then we see how many transactions are there going out of an RDMA and going into an RDMA. And this is DRAM, how many transactions that going into a DRAM. Say this DRAM, there are 13 transactions going into this DRAM. So these are the metrics that can be collected by MGPUSim. So I think this is the basic mode that we want to execute, but I think we want to execute something more interesting. So we can run this mode, we can run a multi-GPU experiment. So to run a multi-GPU experiment, we need to increase the problem size a little bit. So say, I know 64, if the size is 64 will generate one work group. So if we want to use, so one work group can only go to one compute unit. So if we want to be able to utilize 4 GPUs, we have to use, say, something like 256. This is the minimum size if we can at least use some of the unit in 4 GPUs. So we modify this source, then we can run go build to compile the whole simulator again. You can see it's much faster than the first time. Then so this makes the so typically you do not want to model if the simulator is implemented in C++, you do not want to modify something then recompile everything. But in Go, it's not a big problem because compilation is so fast. Now what we can do here is that we can run the same command, but with an extra command called GPUs. Let's run with 1, 2, 3, 4. This is the format how we specify 4 GPUs. The GPUs always start with number 1 because device 0 is reserved for CPU. So you can run, you can see there are 4 kernels running, right? Because they're distributed in 4 GPUs. Now we can run, we can see the Vim matrix, the CSV. Now you can see this CSV is it's regenerated in the new simulation, and you can see GPU 1, 2, 3, 4. They all have kernel time, right? They all have kernel time. Some kernel time is longer, some kernel time is shorter. And GPU 1 actually still only use CU00, and the instruction count didn't change. But if you look at GPU 2, CU00 also run 392 instructions. And we can also see some other information. For example, if we come to this RDMA engine, you can see RDMA 1 gets 27 transactions and RDMA 2 have 9 instructions. So pretty much all the GPUs, all other GPU 2, 3, 4 needs to access data in GPU 1. So this is the information we can get from this the RDMA engine. So this is one experiment with 4 GPUs. Now, what we can do is another example that is unified GPUs. So what is the difference between GPUs and unified GPUs? So if you have program in CUDA, you know, if you try to discover how many GPUs are there in a platform, you can get the GPU ID 1, 2, 3, 4. You know there are 4 GPUs. But sometimes if your code is written for a single GPU mode, it may not be that easy to run with 4 GPUs, right? So in this case, we can use unified GPUs. So for some benchmark that does not support this discrete multi-GPU mode, we can use unified GPU mode. Use unified GPUs to still be able to use multiple GPUs. So if we say use unified GPU 1, 2, 3, 4, we're actually creating a multi-GPU, we're creating a virtual GPU 5, which is actually a combination of GPU 1, 2, 3, 4. But when you allocate data and when you launch a kernel, the driver will take care of which part of the kernel or which part of memory is allocated on which GPU. So let's run it. Pretty much in this case, the result will be pretty much the same. It's unified GPU, not use unified GPUs. So we can run unified GPUs. In this case, we can see. So I think this is a progress bar problem. This is not because there only one GPU is running, I guess. So you can see them. We can verify it, at least to check it if it's running correctly. Yep, it is passed, so it can get the correct result. Then we can check Vim metrics to see how it's going. So is there a kernel running? Yes, there is a kernel running, but there are not, so this kernel is kind of a dummy kernel, so no instructions got executed. And you can see this GPU1 got executed by more, have more instructions. So probably this is just because the GPU driver, they allocate all the tasks to GPU 0. So what we can do here to demo this, how to use unified GPUs, we can increase the problem size by a little bit. Let's change it to a larger one. I will change to a larger one, let's say 64K. I probably will not be able to complete it, but we're going to see at least we're distributing the workload. You can also get a feeling about the performance of MGPUSim. Yeah. So it's actually printing something. So so that's why you can see this progress bar is going down. Or you can see this progress bar is moving. So this is for GPU1, this is for GPU2, 3, 4, and they have evenly distributed workload. All of them get 64 workgroups to run. GPU1 already finished one of them, is moving faster. Then other GPUs are catching up. So it finished pretty much the same time because there are 64 compute units. So all these work groups are actually executing in parallel. So they finish pretty much the same at the same time. But if you have a much larger work input, this value you will see a very smooth progress bar movement. So let's see the metrics. And these metrics will be definitely more interesting. So this is the metrics, and you can see 4 GPUs executing with pretty much the same kernel time, instruction count, all the compute units execute the same number of instructions, and the latencies are different. You can see GPU1's latency is low, and GPU2, no, here it's not GPU2. Then so different shader array has different latencies for some reason. Then GPU2, you can have a better comparison, but I think the GPU2's L1 cache may have a higher latency. And also probably the most interesting thing is the RDMA access is pretty much the same amount to going out from each GPU and going into GPU. So it's a very random memory access pattern. So this is to demo for multi-GPU mode. And other than multi-GPU mode, we have different memory mode. So in this case, we have actually already demonstrated two memory mode. One is discrete multi-GPU. So our benchmark is actually controlling where to place each part of the data. Then the other mode is using unified GPU. So the memory is controlled by the driver. So the driver will distribute the GPU, the memory to multiple GPUs. And then in this case, we do not allow page migration. So we do not allow page migration. So we do not allow the page to move from one GPU to another GPU. But if we use, say, unified, let me run a -h to check it. So it's use unified memory, then it will run in a unified memory mode. So in this case, we start to allow page migration. You will see it actually run much faster, run much slower because page migration is very costly, especially in this case, migrating one page takes a lot of time. So it seems it's very good for GPU1, but it's not good for other GPUs. Yep, other GPUs start to move, and then it's kind of good for GPU1, then GPU2, then it's bad for GPUs 3 and 4. Then, yeah, the result can still pass. So you know this is a valid implementation. Then we can run vim matrix.csv. Then you can see, okay, then this time we see very different memory access time. So GPU1 definitely have some advantages. And GPU2, 3, 4 has different have some disadvantages. So this is memory mode. So we have 3 different memory modes: discrete multi-GPU, so user can control it; unified multi-GPU, the driver controls where to place the data; and the unified memory. The unified memory which allows page migration. So this demonstrates pretty much everything about the basic running mode about MGPUSim. Then there's something that I want to also introduce to you, but I cannot use it here because I do not have the environment to run it. So I can leave this environment. Let me close my virtual machine. And I'm going to use my terminal here to use one of our server. So this is our server. Then we can run it, or I have some simulation running here. We have some environment that is configured here. Let me see which one it is. Oh, we have a bit. So here I can show you the visualization tool. So the visualization tool is in this in this folder. In this path, this is in gitlab.com akita viz. So there are instructions about how to run it. So let's run a visualization. Let's run a simulation first, so that we know what is going on, how we can collect traces. Let me clear it. And then let's go to the MGPUSim here. That's the installed MGPUSim, and I think it's currently in master branch. Yes. So let's run a sample. Then another interesting workload is concurrent workload and concurrent kernel. Concurrent kernel actually means we're running two different kernels on one GPU. So let's run it. Concurrent kernel. Then we can see the main program here. This is the main program. You can see we have one FR benchmark and one Pythonic scored benchmark. And they select GPUs, and they both select GPU1. So they will run on GPU1 together at the same time. So we can run go build just to make sure it is the most recent version. Then we can run this concurrent kernel. Timing with trace with we do not want to progress bar. That's not a big problem. Let's run with progress bar. Yeah, we need to set some environment variable. I think I have set it. Let me set here. Yep, this is the last time I set it. Now we need to set also the password. Okay, so we have the environment configured, so we can run this concurrent kernel workload. You can see, okay, it's running concurrent kernel. It seems the Python sort is running very fast while the FR is running very slow. So if you start to collect trace, you will see this line. So it will trace is collected in database, this particular database. Then it's actually a MySQL database, and it's actually stored. It's for every experiment, it is stored there. So let's run here in the server. The server is also developed in Go. So let me just compile it so that we can guarantee it's the most recent version. Yep, that side already finished. Okay, this side is also finished. So we can run this server. Then this is my past. This is another database. But since we copied this experiment ID, we can select a path, a port, say HTTP 12010. Okay, then we can run on this port. We can run it. Then in our browser, we can start this browser. We can start this one at this URL. This is where we are hosting it. So we have this visualization tool called Dyson, and Dyson is just a visualization tool designed for MGPUSim. And you can see at the beginning, we see this overview panel, which shows a lot of different components. It's pretty much all the components you will executing some tasks. So you can see here, we have command processor, we have dispatcher, we have direct memory accessor, then we have different DRAM banks and DRAM itself. Then we can go to the next page to scan through all the just different type of components. You can see here, we start to see L1I address translator. Then we can see compute unit. Now we see L1S cache. This is a cache. Then we can see different. So this is a cache, and we have two curves. And you can select what metrics you want to see in this curve. For example, here we're seeing this incoming request rate. Incoming request rate, so how fast that the request arrives at this particular component. So here we can see it's 3E7. That means 30 million requests is arriving at this component per second. So can it match your expectation? It requires some domain-specific knowledge about which component it is. Now, other than incoming request, we have this request complete rate, like how fast I'm completing request. Average request latency. You can see this blue curve is average request latency. Okay, so this latency is actually low here and high here and here. Why is 0 there? Is probably because there's no task running. Now we can see buffer pressure. How many requests are there in a buffer at a given time? So you can see this value is a very small value, right? So I think L1V is not representative. Say this L2 cache is probably more representative. So here we can see 5, okay, right? Buffer pressure is around 5. So at this time, there are 5 requests waiting in the buffer. That means it's a little bit bottleneck for the current program that you are running. So I'm using my mouse scroll to zoom in and out of the whole simulation. You can also reset zoom to reset the whole simulation scope. And also, if you care about, say, I want to know what's going on with all the L2 caches, you can simply type L2. Then we'll filter out all the L2 cache. Also, L2 TLB is also here. But you can see all the L2 caches, even L2, GPU2 L2 is here. So it's probably, for some reason, we need to flush it. So that's why it's probably also have some average request latency. But you can see the pattern for GPU1 and GPU2 is very, very different. Then say, okay, we can zoom into here. Then say it's very interesting that we see this buffer pressure. There's a buffer pressure that is very low. So probably there are not a lot of transaction going on in this L2 cache. But if you want to know, okay, what's going on in this particular position. It's probably just because there's one transaction coming here. So we can zoom into a really small region. Now we can click on the title of this name. Now it will go to another view. Okay, this view is, the bottom part is called component view. So component view is showing all the tasks that are executing in this component. So we can see this L2 4. This force L2 in GPU1. And if we hover on it, you can see on the right side, you can see here, it is a memory read request. So this is request in. So this is request coming into this L2 cache. And this is request out. So this is a request coming out of this request L2 cache. So you can see this request is nested. These tasks are nested. So in order to fulfill the outer task, I'm doing the inner task. Pretty much I can say this is a read miss because the read out takes the majority of the read request in task. So sometimes we also want to know, say, what action this request triggers on the DRAM side. So we can click on this read request. Then you can see this task is, this part is enabled. So this is called task view. We click the request out task, it becomes the current task. We're showing what are the subtasks of this current task, and we're also going to show we're also showing the parent task. So you can see the parent subtask is a request in arriving at GPU1 DRAM 4. Then we can click on it to zoom one level down. So you can see this is a request. This is a zoom. This is something called a sub transaction, and in this sub transaction there are two commands. One is activate and one is read precharge. So pretty much we can say at this moment the DRAM is not busy at all. It's occasionally there are some requests, but there's no request going on. You can see here, the DRAM is handling a lot of requests. So there are some bottleneck at this moment, but there's no bottleneck here. So then I'm curious what's going on here. Okay, so I can click on this task and you can see the DRAM waits for a long time before it can activate this row and write precharge it. So this is probably a lot of write requests. So in this case, we also want to know, say, what's going on with this request? Why there are so many requests arriving at this DRAM? So we can go to click on the parent task to go up towards this task tree. Now, see here, we're going to the L2 task. As you can see, okay, here it's very interesting. This is a flush request. For some reason, this L2 needs to be flushed. And we can go up one layer and see this request in flush task, and there's no parent task. So this is probably just a not good example here. So we're not really capturing some task that is triggering this flush task. It's some control command. But we can see here, what's this one? This is a flush request, another flush request, but not doesn't have anything else. So let's find another regular transaction. So we can go to the parent task. We can see this, we're going to L1I address translator. Okay, so this is a L1I address translator. So L1I address translator on one side will do this translation request, right? You can see this amount of time is spent on doing translation, and this amount of time is spent on read request. So you can get the feeling about this ratio. So you can see this ratio. The translation is very quick, while the read request actually takes the majority of the time. Then we can go up, see what action is triggering. So this is L1I cache. L1I cache is above the address translator, so it's a virtually addressed, virtually tagged. You can go one layer up, one more layer up. Okay, we're going towards this ROB, reorder buffer. Between the cache and the compute unit, there's a reorder buffer. You can see it's very interesting to look at what's going on in this reorder buffer. So this reorder buffer has some tasks. Okay, now we can keep going on. Finally, we arrived at the compute unit. The compute unit is an interesting point, and we can see what tasks are executing here. Then, so So here is what's going on. So you can see these are pretty much from two kernels. How I know it, you can see this purple one is a work group. This green one is a wavefront. In this kernel, one work group has 4 wavefront. In this kernel, one work group has 1 wavefront. So it's pretty much 2 kernels. We're running concurrent kernel and we know it is running in one CU, but it's not overlapping. It's just, we probably can tune the problem size to make it overlapping, but in this case, it is not overlapping. And we can see what's going on in one wavefront, okay? If we click on one wavefront, you can see those are the things that within one wavefront. So if I hover on this, you can see on the right side, this is a fetch. So this is instruction fetch. So it's fetching some instructions. And so you can see there are different type of instructions. So this is scalar instruction, these dark green ones. Then these are special instructions, probably synchronization. These are VLU instructions. This is for real calculation. These VMEM instructions for memory operations. Okay. Then this work group read request. You can see there are a lot of read requests requesting from the memory system, and this is a write request. And this is wavefront itself. So by doing this, you have a very good idea about what is going on in this wavefront that's executing in this compute unit. So we can actually keep going up. The performance is can be a little bit challenging, but the problem size is not very large. When the problem size is large, you probably want to only take part of the trace. You can go up. Then you can see we are arriving at this driver, and we can have a big high-level overview about what's going on. So here you see we can see we have this flush command. So this flush command comes from the driver. Is just when the kernel complete when the kernel completes, we need to flush it. Then we need to launch a kernel. There are so many kernels that are executing. You can see, so pretty much this is the FR kernel. These are the Pythonic short kernels, because Pythonic short kernels are short. FR kernel, there's only one kernel, but it takes much longer time. Then you can see some, this memory copy is, you can see this is memory copy device to host, and this is memory copy host to device. And we have different tasks. Then these are so this in this device to host command, where actually each request is copying one page. So those are the page copying process. So you have a very high level idea about what is going on in this whole simulation. And the root task is the simulation task, and the simulation task doesn't have any parent task. And you can see on the right side, the duration is 170 microsecond. It's give you a high level view about how long time it takes. Then we can go back to the click on Dyson, then we can go back to the original view. Then you can start back to find some high level trends so that you can dig down into the detail. So as a summary, I want to say MGPUSim has a long development history that we have been developing it for more than 3 years, and we care about the user experience of using a simulator. So it has a lot of features, unique features like address translation, like multi-GPU execution, like concurrent kernel execution, and we have actually a lot of free-flow tools that can help a user using a simulator. And the visualization tool is only one of those such tools, and we have other tools to support it. So if you are interested in MGPUSim, you can send me email, and I'm happy to answer your questions. And feel free to give it a try. Thank you.